Okay, I hope this slide is visible. Fine. So till last class we were discussing about different tracking methods, how we can do object tracking. We have discussed different methods for that. Now from today's class, it would be a new topic. We'll be discussing about stereopsis. Now stereopsis is a method that is used for reconstruction of a 3D scene, right? And we'll see some basics of the stereopsis method in today's class. Okay, so what do you exactly mean by 3D reconstruction? So let's say you have in the very first introduction class, we had discussed some examples of 3D reconstruction. So 3D reconstruction means, let's say you're given a few images, right? So it could be two or more images. Now, given those images, and let's say all those images are images of the same scene. Now, when I say scene, what I mean is, I'll just write it down here. Scene. Okay, so what I mean by scene is the actual 3D world, or the view that you have of that 3D world. Okay, so the actual 3D object along with its surroundings is what you call as the scene. Okay, so whenever I say scene, you need to understand that it's the 3D object and its surroundings. So now for reconstruction, what that means is, now let's say you are considering different images which are capturing the same scene, okay, but at different viewpoints, right? And given such images, a set of images, how do you reconstruct back that particular scene is what you call as a 3D reconstruction. And there are various methods by which that can be done. And so we'll just discuss about some of the broad categories by which it is done, and just the basic concepts in today's class. So let us say you have, let's say you have an image here, right? This is a 2D image of a particular scene, and since I cannot draw the scene here, I'll just represent it as a 3D coordinate over here. Okay, so over here this represents the 3D space which is containing the scene. So what we need to do is, this image, let's say, is capturing the particular scene, okay, which can be represented in this particular 3D world coordinate, right? Now, when I say this 2D image represents this, and when I say I want to reconstruct from the 2D image, I want to reconstruct the 3D scene, what I mean is that if, let's say, I have a point in the 2D image, right? Given a particular point in a 2D image, what I'm trying to do is I'm trying to find out what is the corresponding 3D point, okay, for this particular 2D point. So given a point in the image, okay, how can I reconstruct in the sense, how can I find what is the corresponding point in the world coordinate, or corresponding to that particular 3D scene. So that is basically what you call. So for each and every point that you consider on the image, you can accordingly calculate the corresponding points, and finally, so when all those points are calculated or determined, you can kind of reconstruct that whole particular 3D object or the scene that we are considering. Okay, so this is how the problem translates to. And if you remember, we had in one of the earlier classes, we had already seen what do you mean by the different, 2D coordinates, the 3D coordinates, and what do you mean by the world coordinates, the camera system, the retina system, etc. And we had seen how we can do the conversions from one coordinate system to the other. Okay, so just try going through those lecture classes or the notes that you've taken once again, and try familiarize with those concepts once again, because that will be used over here. Okay, so what we'll be discussing here would be about how we can make use of all those concepts in order to find what is the corresponding 3D point which corresponds to each of the 2D points that we are considering in the image. Okay, so, and that particular process, or that particular approach is what you call as reconstruction, right? A 3D reconstruction. Now, this kind of 3D reconstruction where you try to find out what are the corresponding points in a 3D scene with respect to points in an image, you can there are different ways by which you can do that. So broadly you can say that there are two methods here, just broadly. So one method is called as the stereopsis, okay, which we'll be studying in today's class. And another method is what you call as SFM. So SFM stands for structure from motion. Structure from motion. Okay. So broadly we can classify these as the stereopsis and SFM. Now, what do you mean by stereopsis, right? So stereopsis means, let's say you have two images. Usually you call it as stereo images, stereo camera. These are some terms that we will be, stereo vision. These are some of the terms that we would be coming across later. So what stereopsis means is, let's say you are given two images. Okay, so let's say you have two different two images, okay, two different images, but these two images represents the same, or it takes the same picture or image of the same scene, right? Now what this concept of stereopsis says is that, let's say you are given two images of a scene, how do you reconstruct the 3D view? So from this image as well as from this image, I want to find out what is the 3D view corresponding to that, or what is the 3D scene corresponding to that. So what that means is, as I said earlier, when you say you're trying to reconstruct a particular object or a particular scene from an image, means what that means is you consider different points in the image and then you try to find out what are the corresponding 3D points with respect to right. So in the same way here, given two images, when you're trying to use these two images to reconstruct that 3D point, what we do is, or what we can say in other words is that, let's say I'm considering, or I have some point, let's say XL, okay, XL, and let's say I have another point XR, right? So L and R, which stands for, let's say, the left image and the right image. So from XL, you have a point here, and correspondingly you have another point XR in the right image, and from this point XL and from the point XR, you are trying to find out a point, let's call it capital X over here. So this is the 3D point. So given these two 2D points from these two images, which takes two different viewpoints, how do I calculate the coordinates of the of this particular 3D point? Okay, so that is the basic basic problem statement when it comes to reconstruction in stereopsis. So we are talking about stereopsis over here, right? Now, in this case, one assumption that you make is that, you can assume this as, let's say you have a camera over here which takes a particular viewpoint, and then you have another camera which takes another viewpoint but of the same scene, right? So that means I have a camera which I'm using here, I have another camera which I'm using in this case, right? And the camera parameters that we are using, let's just denote that the camera parameters is given by P over here and Q for this particular camera, right? Now what we assume is that the camera parameters P and Q are known to us, or that it has been already pre-computed and it is calculated and kept, okay, or it has been already determined, or let's say it is already known to us. So once you know the camera parameters and you have the information of what are the corresponding point pairs between two images which represents the same point in 3D scene, then the actual task of reconstruction is to try to find out which is that particular 3D point, or what is the location or position of that particular 3D point. Okay. So this method, it's called as stereopsis, and that's the first method. And as I said, you are considering two images in this case. Now, the second method that you have is called as the SFM, or the full form of that is structure from motion, right? Now, in the SFM method, what we use is the input images. Okay, it's not going to be just two images. We will have multiple input images. So in this case, what happens is instead of having just two images, you may have multiple images, right? And from all these multiple images, what we do is we try to reconstruct. So we make use of the information of all this in order to get the 3D reconstructed scene, right? So the details of this SFM approach, we'll be seeing that later. What you need to remember now is that unlike stereopsis, in this case, we make use of multiple images, right? And that is one point. And another point is that here in the case of SFM, or the structure from motion, when you're using multiple images, right? The camera parameters, it need not be known to us. Even if we do not know the camera parameters, it is fine, okay? Because we have the information of all these multiple images in order to guide us to find out where exactly is this point capital X, right? So the camera parameters may not be known to us. It need not be known to us, okay? And what we do is we make use of all these multiple images in order to find out the point X. And not just that, we'll also see that, in some cases, we can actually even compute the camera parameters if it is required. That means let's say we do not know the camera parameters, but we have a bunch of images which are different viewpoints. So when I say a bunch of images or different images, what I'm saying is that it's not just this same image from the same viewpoint. It would be different viewpoints. Only then you will get different information. If it's the same viewpoint, you do not get any different relevant information in order to reconstruct the particular object or scene. So you need to have images from different viewpoints so that you can take the information from all of that in order to calculate the 3D point, or in order to reconstruct that scene, right? Now, as I said earlier, in the case of the structure from motion, one thing is that we use multiple images. The second point is that here the camera parameters need not be known, right? And in cases where it is not known, you can use that. And at the same time, you can also even compute the camera parameters along with finding this position of x2, okay? So, in this class, we'll be discussing only about stereopsis, where we use only two images, and later we'll move on to the SFM approach. So if you see where exactly do you prefer to use stereopsis method, or where exactly do you prefer to use the SFM method? In the case of the stereopsis approach, we prefer that for reconstruction purposes, if we know for sure what are the camera parameters. So that means, as I told earlier, we need to know what are the camera parameters if we are going by the stereopsis method, because it makes use of these camera parameters in order to find out the position of the 3D point, right? So therefore, a prior knowledge of the camera parameters is important, right? So in cases, or in applications where you know the camera parameters, or let's say the camera parameters do not change over a period of time while the image acquisition is going on, okay? Or let's say we know the camera parameters precisely, and these parameters are fixed throughout the image acquisition. So in such a case, we can go with the stereopsis. Okay, so because what happens is that it is important that we know the camera positions or the parameters precisely, because let's say even if the camera position changes, or let's say we are moving it slightly, then what happens is the camera parameters may change, right? And so since the first step is a computation of the camera parameters in this particular method, the stereopsis method, what happens is if the camera parameters change at some point of time, then again from the beginning it has to be recomputed. The camera parameters will have to be recomputed. So the assumption that we make is that the camera parameters do not change over time, in the sense that if it is, let's say, in terms of position, the camera positions remain the same, okay? Or if it's in terms of any other intrinsic or extrinsic parameters, we are assuming that it is fixed over a period of time, and we assume that we already know what are the parameters. So in such cases, we can go ahead with stereopsis in order to find out the particular location of the 3D point. And as I said earlier, for stereopsis, we make use of only two images. Now, on the other hand, when it comes to the SFM method, we usually use this method if we do not know what are the camera parameters. Okay, so if we do not have an information of the different camera parameters, then we usually go with the SFM method. So if you look at this, see, you have multiple images that you're using, right? And and all these multiple images shows different viewpoints of the same scene, which means that the camera parameters would be different for each of these images which we have considered here, right? So even if you do not know all the camera parameters over here, we still can compute, or we still can do the reconstruction when it comes to the SFM method. Okay, so that is how the preference goes. So in you can, so when you say stereopsis, okay, so in today's class we'll be learning about stereopsis, right? So when you say stereopsis, or when you think of stereopsis, or another term which you may be more familiar with, maybe stereo vision. So how you can interpret it, or the basic concept is that you can just take the case of, or an example of, the human visual system, right? So that is, we have two eyes, and these eyes are positioned at slightly different locations. So you can just imagine these two camera images. Now these are images which are captured by two cameras. So let's say I have a camera position here. Okay, let's say this is one camera here, and this is another camera here, and it is trying to capture these two images of the same scene, right? So you can think of these as two eyes. So you can say that those eyes are positioned slightly at different positions, okay, but it is looking at the same object over here. And when so just with that stereo vision that you're having, that is just by taking this two images from these 2 points, what you see is that our eyes can easily find out any relative distance, or the depth of a object, etc., right? So the distance information, or the depth information, is something that can be calculated with this stereopsis concept. Okay, just like how the humans can also, when they look at objects, they can understand how far or how close the objects are, maybe with respect to something in the surroundings, or with respect to each other, or so on, right? So that same concept is being used in the case of stereopsis method also, where these two camera systems actually are, you can say, it can be called as equivalent to the eyes that we have in the human visual system. And now here, since we consider these cameras as the human eyes over here, and as I said, these would be slightly different positions, right? So that means the camera parameters in these two cases, that would be different, right? And using these parameters, or knowing what are these parameters, okay, we can try, or we can use that in order to reconstruct the particular 3D point. Now, another thing that you can observe is, as I said, the human visual system is able to capture the depth information, or the relative distance between objects, right? Now, if we close one of our eyes, what happens is that the depth information may not be that precise. Okay, the actual distance that is being seen or being perceived may be different when you just close one of the eyes, which means that if I'm considering only one image, okay, or the output of one particular camera system alone, then the actual depth information which I can calculate from that alone would be different. Okay, so therefore you need at least two images in order to calculate the depth information. So I'll just explain this further. So let's say you have only one image over here, right? So this is my, let's say, my 2D image, and let's say this is some point which I am considering. Okay, it's a 2D point that I have, and my 3D point lies, let's say somewhere over here. You have the coordinate system, and let's say my 3D point. Okay, let's say my 3D point lies over here. I'm representing it by capital X. Now, one more thing which I would like to tell you is when you're moving further on this topic, we'll see that the small letter notations are used for the 2D points, okay, and the capital letters will use it for the 3D point notations, okay. So let's say I'm considering a particular point in the 2D image which is given by X, and let's say the corresponding point of that in the 3D world is this capital X, and which is given by this one, right? So, and let us assume that we have only one image here, okay, with a point X, and the actual 3D point, as I said, is this. Now, we have studied the concept of the pinhole camera projection model, right? So in that pinhole camera projection model, we learned that, okay, this is represented by X is equal to Px. Okay, so using this model, what we know is that here, if I try to join this line, okay, if I try to join this one over here like this, okay, if it is only one image over here, we can say that we can't exactly say where exactly this point capital X may lie. Okay, so you know that capital X lies along this particular line here, right? But you're not very sure where exactly it is. That means it could be maybe somewhere at this point. Okay, let me say I'm calling it x1, or maybe it is at some point x2 over here, or let's say it is at some point x3 over here, and so on. So the only information that you have is that the point that we want to find out, that is capital X, lies along this particular line. Okay, but you're not very sure exactly where it is. But let's say you have another image, you have a second image here, and let me just draw it this way, right? So this is my second image over here. So let me just write it as XL to say that, okay, this is my left side image point that I'm considering. Now, if I have a corresponding point, a point which corresponds to this particular point, if I'm having that, let's say, let me call it as XR here. Okay. Now, if I have a point XR in this right image, okay, using the same pinhole camera projection model, I can say that, okay, the image, the actual 3D point corresponding to this XR will also lie in this point, in this line. Okay, so using the camera projection model for this particular case, or for the first image, the left image, I'll just name it as the left image and the right image. So for the left image, I know that the 3D point X lies along this line, and for the right image, I know that this 3D point lies along this particular line. Okay, so that means the point of intersection of these two lines will actually give me, by that I can conclude that this point of intersection is actually the point that I'm looking for. That is the 3D point X. Okay, and this would be in the world coordinate system. So this is the basic concept of the stereo vision. That is, when you have two images, you can consider different points within that images, and then we can try to just use the pinhole camera projection model in order to project the lines, okay, into or project the lines forward, and the point of intersection of these two lines would be the 3D point that we are considering. And as I said, let's say if you're considering only one image, okay, then you do not have the exact depth information where exactly it will lie, right? It will be what is the exact depth information, or the distance that we have from this particular image plane is something which is not known to us. But with the help of a second image, what happens is we get an extra information regarding the point, and that extra information is found out by finding what is the corresponding point of x in the right image. Okay, so we find that out, and then we can again use the camera projection model over here and find out that the capital X or the 3D point is basically the point that we are looking for. Okay, and this is the basic concept of stereopsis. Okay, and we'll be going through the details of that in the corresponding slides. Okay, so now we'll be discussing in detail about the stereopsis method, and it's also called as the stereo vision method, right? And this stereo vision, so we are saying stereo in the sense we are using two images. So all these stereo vision, stereopsis, all these or stereo cameras, all these come under the same process over here. Okay, so this stereo vision, the method can be divided, or it can be thought of as two different processes. One is called as the fusion and the second one is the reconstruction. So in the first method, what we do is it's a fusion of features which are observed by two or more eyes. Now we are saying two or more eyes in the sense, what we mean is the camera systems that we are using. Okay, so it could be two or more camera systems is what it means. So what we are doing here is the first step is fusion of features. That means this particular fusion process will tell us whether the 2D image point, let's say P. Okay, I'll just refer to this particular figure over here. Now what this figure says is that this P, okay, that this is one point in one 2D image, and P dash is again a point, a corresponding point in another image, and both these images are trying to capture the same scene. And let's say the scene that I'm considering is has only one single 3D point, so I'm just considering one single 3D point case over here. Okay, and that is given by capital P. Okay, so what the fusion process says is that, okay, it will tell us whether the 2D image point P, okay, and this P dash, whether these two represent the same 3D point P or not. Okay, so what we do is here, as I said, it is a fusion of features. So fusion of features means by fusing the features which are coming from these two images, okay, corresponding to P and P dash, we what we do is we try to find what is the corresponding point pairs. So in this particular example, the corresponding point pair is PP dash pair. Okay, so here in this example, what we have is a PP dash pair, okay, which represents this and this. This is basically the small p. Okay, so I'll just put it here because capital P represents the 3D point, right? So what we do here is we try to fuse the features that we have extracted from both the images, and from those features we try to find out which are the corresponding point pairs P P dash, which represents the same 3D point P. Okay, so I can also say what that means is, let's say I am given a particular point in the first image. Okay, then I can try to find out what is the corresponding point in the second image. Okay, so that means given P and the capital P, I should be able to find out this P dash, or even if the capital P is not known, actually you have matching methods in order to find out from P. By using the features, you can try to find what is the corresponding pair or point P dash, okay, in the second image. Now, once we know what are the point pairs P P dash, what we can do is that is this P P dash over here. Okay, you can just project these. Okay, as shown over here, and you can try to find out what is the 3D point. So once we have this information, then you can just project these and find the 3D point. Now, how do you do these projections? Now this O and O dash are basically the camera centers. Okay, so by joining these lines, what we join point P with the camera center O and just project it. And again, we draw a line from P dash to O dash and project it. And the point of intersection of these two lines would give me P. Okay, so that is a concept that we are using here, right? So in this example, what we have considered is just one point, one 3D point. Okay, so here this 3D point, yeah. So here this 3D point, right? This is in the 3D, world, and this P and P dash, what we are considering is actually the 2D points which are within an image. So what we are doing is, if I just try to draw it here in this terms, okay, the P and P dash would write, let's say somewhere over here and here, okay, is the P and P dash point, and this is the world coordinate over here, and I'm trying to find out what is P. Okay. So so if we are using a single image feature, okay, as we just saw earlier, the matching would be easy. That means, see, in this case, we considered only one single point here, and we then tried to find out what is the corresponding point in the other image, and using these 2 points, we just joined the lines, and we got the point of intersection as capital P. And it is as simple as that if you're just considering a single image feature. But as you said, I mean, we don't just go about with one single image feature, because what we are trying to reconstruct is not a single point. Okay, it may be an object, it may be a scene with several points. So what we do here is, when you have thousands of features, let's say, so when I say features, these features can be extracted, or it may be found out using different edge features or gradient features, or etc. Okay, but let's say you have an image and you have multiple image features, then using the above concept of trying to project the lines and finding the point of intersection, that becomes very difficult. Now, as an example, you can just look at this particular figure. So in this figure, you can see that we have 4 points. I can call it A, B, C, and D. Okay. So let's say I have 4 points in the left image. And in the second image, the corresponding point pairs that I have is, let's say, A dash, B dash, C dash, and D dash. Right. Now, in order to find out the corresponding 3D points in the world coordinate, what we do is, as I said earlier, we try to join this point along with the camera center and project it. Again, this point we try to join with the camera center and project it, and we do that for all the points. Now, what happens as a result is, so when I'm projecting these lines over here, as well as when I'm projecting these lines over here, what we see is that there may be multiple points of intersection. In the previous case, what we saw is there is only a single point of intersection, because you're considering only two lines, and therefore that particular point, by default we just take it as the 3D point, and it's good to go. But in this case, what happens is, you have multiple image features, or let's call that points over here. Let's say you have multiple image points which are given within the image, okay, or both images, the first image as well as the second image. So, and if we follow the principle of pinhole camera model projection, we back propagate all the lines as shown over here, and we get these multiple points of intersection, right? So when you get these multiple points of intersection, to find out what exactly is, now the exact point is A, capital B, capital C, and capital D. So in order to find out which among these points of intersection are the actual points of intersection, would be a task, right? That would be something that has to be found out. So what happens is this process of trying to find out these 3D world points is not as simple or straightforward as was discussed earlier, because as we have more features and more points, we see that it becomes more complicated, and we will have to incorporate more steps in order to find out what exactly are the points, the actual points of intersection, these capital A, B, C, and D. Now, another point here is that, so let's say there are some errors in computing the 2D points from the image features. Okay, so sometimes due to some errors, what happens is the lines may not intersect at all. Okay, so here you'll get the lines intersecting at those exact points only if you have also found out the corresponding image pairs in those precisely. Okay, but what happens is, since these are points that may come from let's say some other prior feature processing or feature extraction steps, what happens is there may be some errors in computing this, and therefore sometimes the lines may not intersect, and sometimes it may be due to error in calculation. So what that means is that we cannot always guarantee that the two lines that we are drawing in that 3D space, okay, will always intersect. There is no guarantee, because there is always this error factor that needs to be taken care of. Okay, so now we'll see a very brief outline of the stereopsis method. So first what we'll do is we'll be discussing about epipolar constraint. What is epipolar constraint? And we will see how important epipolar constraint is for reconstruction, and we'll also see how it actually helps with reducing the computation time, or the computation complexity of the images, I mean of the processing step. Okay, we'll see that later. So epipolar constraint is a very important concept of reconstruction. Now another concept which is important is the binocular reconstruction, that is the process of reconstruction itself. So as I said earlier, when you say reconstruction, what that means is, how do you find a 3D point using two or more image points, okay, or 2D points, okay, or you can say, how do you compute the 3D point using intersection of two lines, just like how we just saw earlier, right? So that is called as a binocular reconstruction. And another term that you need to be familiar is the binocular fusion. So binocular fusion means, the first step, if you remember, what we were doing is we were trying to find out point pairs, right? That means given a particular image, here if you have a 2D image with, let's say, a particular point P, and then you have, so this, let's say this is the left image and this is the right image, and you have another point over here which is, let's say, given by P dash. So trying to find out which exactly is the point which is corresponding to the same 3D point capital P is now that particular process is what you call as binocular fusion. Okay, so fusion is nothing but trying to identify what are the corresponding points x and x dash. So here, when you go about this stereopsis method, what we do is the very first step would be to calculate the camera parameter. So as we saw earlier, when you are going about with stereopsis, here we assume that the camera parameters are known to us, right? So if the camera parameters are known to us, that may need to be computed. So the very first step is to find out what are the camera parameters. Now, after we know that, the next step that we do is fusion. That means then the next thing what you do is you try to find out, given the points in P, what are the corresponding points in the right image, that is P dash. Okay, so finding the the point-to-point correspondence or the corresponding point pairs is the second step, which is known as the fusion. So then you go about fusion. Now, after fusion, that is, after you find out the corresponding point pairs, what you next do is you try to reconstruct that. Okay, so the reconstruction method just follows this. Okay, so even though this is the way by which we go ahead with trying to do a reconstruction using the stereopsis method, while we are discussing this topic, what we'll do is first we'll discuss about what is epipolar constraint, then we will discuss about what is the reconstruction, how the reconstruction is done, and after that we will be seeing how the fusion is done. Okay, so that means first we, before fusion, we will just discuss how we can calculate the 3D, point over here, right? And then we will discuss fusion. Fusion means how we can find out how to, points can, the corresponding points, point pairs can be found. Okay. But remember, this is the procedure. First, the camera parameters needs to be known, and then you go about with fusion to find the corresponding point pairs, and then you go about with reconstruction to finally determine what is the capital point P, or what is the 3D point P. Okay. Okay, so now we'll see what is epipolar geometry. We'll just get familiar with this particular concept of epipolar geometry. So this epipolar geometry is an important concept in order to find out the corresponding point pairs P dash, right? So if you look at this figure here, okay, if you look at this figure here, what we see is this O, okay, represents what is the camera center of the camera which is placed over here. Okay, and this O dash represents the camera center of the camera which is placed here. So you have two cameras, okay, which is taking two images of the same scene, in which capital P is a point of that 3D scene that you are capturing. Okay, and let's say these are the image planes that you have corresponding to each of those cameras. This image plane is given by pi, and this particular image plane is given by pi dash. There is a dash over here, it's given by pi dash. And O is basically the camera center over here and on the left side, and O dash represents the camera center on the right side. Okay. Now here, this camera here, as I said, we are considering only one single point in the 3D world, right? So if this camera is trying to take an image of this particular point P, the corresponding, let's say the corresponding point in the image plane can be represented by small p. Okay, so similarly, when the camera tries to capture an image from this particular viewpoint of the point P, the corresponding point can be denoted by P dash. Okay, and pi and pi dash, as I said, these are the image planes, and basically that retina coordinate system that we have seen earlier. Now, one thing that we have learned before, or that we have seen before in one of the lecture classes, is that this O, P, and this capital P over here, they all lie in a straight line, right? That means if I join, so this is, as I said, this is the image of the 3D point P, right? So if I try to join the camera center with the image point P and project it, what happens is this capital P, that is the 3D point, will lie along that particular line. Okay, so similarly, we'll also what we have also seen is that this O dash, P dash, and P will lie in a straight line. Okay, so that is something that you need to remember. So if you look at this whole figure, what we see is that we have different points here. Now we just saw 5 different points. That is, I have O dash, which are the camera centers. Then I have P dash, which are the image points. and then I have capital P, which is basically the 3D point, right? Now all these points together constitute what you call as the epipolar geometry. Okay, so here what you can consider is all these together. When you join together, you get a plane in 3D. Okay, so it's a 3D plane. You can if you remember, we had discussed about 3D planes in the world coordinate system in the previous class. So here, if we try to join all these points together, okay, you get a 3D plane, right? And you can represent that in terms of the homogeneous equation here. And the planes that you see here, pi and pi dash, are basically the 2D planes, because these are basically the image planes or the retina. Okay, so again, one thing you need to recall is that two planes, given a 3D, in 3D space, always two planes will always intersect. Okay, so just like how you say in 2D space, two lines will always intersect. In the case of 3D, equivalently, we can say that two planes will always intersect. So if we say two planes will always intersect, what that means is, now you have this image plane here and you have the epipolar plane over here, right? So that means this image and this image, the image plane pi and the epipolar plane will intersect, okay? And another thing is the planes always intersect with at a line, right? So that line of intersection, instead of in the case of 2D space, we say that when two lines intersect, you have a point of intersection. In this case, when two planes intersect, you have a line of intersection. So here what happens is that when you have these two planes intersecting, you get a line of intersection. And let's say the line of intersection is given by L in this case. And when the image plane pi dash and this epipolar plane, the line of intersection in this case is given by L dash. Okay, and this L and L dash is what you call as epipolar lines. Okay, so this L dash is what you call as epipolar line. And then another 2 points that you need to remember is E and E dash. Basically, E and E dash is what you call as epipoles. Okay, so it is basically the point of intersection of this particular line, that is the line joining O and O dash. Okay, this particular line along with the image plane, right? That is E. Similarly, E dash is the line, is a point of intersection of this line joining O and O dash and the image plane pi dash. Okay, so these are the different parameters that you need to be familiar with in the epipolar geometry. Okay, so now we can say that let's say given a 2D point P, okay, so let's say you have a 2D point P over here, right? And this P is actually the image of the 3D point P in the world, right? Or in the world space. So given a 2D point P and a 3D point P, we can say that the corresponding 2D point P dash, which corresponds to this particular point here, right? The corresponding point P dash will lie on the epipolar, line. L dash. Okay, so this is another important concept that you need to know. That is, if I am given the image point of one image plane and the 3D point P, then I can say that the corresponding point in the image plane pi dash, which is given by P dash, will lie on the line, epipolar line L dash. Okay, and as I said earlier, you can find out which are the lines over here. If we know which is the epipolar plane and given the image planes, we can easily find that out. So one, this concept, this particular concept that this P dash will lie only along the line L dash is very important when it comes to reducing the computational time or the complexity. That is, let's say if I'm using just some conventional approach, okay, and we know that P dash over here lies in the plane pi dash, okay, because that is the image plane, and P dash lies in this particular image plane. So let's say if we are not using this concept of epipolar geometry, and so that means uh, when you are trying to search for where exactly is this point P dash, we do not know where exactly it is within the image plane. So you may have to scan the whole image plane or search throughout the image plane in order to find out where exactly is P dash, right? So, by using the conventional approach, what we do is, given this image plane, we'll have to search the whole image plane in order to find out where exactly is P dash. But instead, if we are using the epipolar geometry or the pinhole camera projection model, then what we can say is that P dash will lie along this line L dash only, right? So that means the area or the space where I'm searching for P dash can be limited to only along this line. So instead of searching the whole image in order to find out where exactly is P dash, all that I need to do is I know that P dash lies along this line L dash, okay, and you need to search for P dash only along this line L dash. So in that way, it will help with reducing the search region of the image very significantly. And this is one advantage of using the epipolar geometry. So similar to that, if let's say you know what is the point, you have the point P dash and the capital point P, okay, in a similar sense, we can say that this point P, that is the corresponding point of P dash in the image plane pi, will lie along the epipolar line L. Okay, so it goes both ways, right? So, and this is the basic concept of epipolar geometry. Okay, and now just some terms. You're already familiar with, what is the basic concept. Just some terms that you need to remember here. One is baseline. So what baseline means is that you know that these are the optical centers, or the camera centers, O and O dash, right? So this line which joins O and O dash, this particular line is what you call as the baseline. Okay. Now, the second term that you need to know is epipoles. Epipoles, which are denoted by E and E dash. So you can say that, as I said earlier, if you look at this point E, okay, which is present over here, okay, it is actually the point of intersection of this baseline on the image plane pi is given by E. And the epipole E dash represents the point of intersection of this baseline, okay, with the image plane pi dash, right? So you have E and E dash, right, which are called as the epipoles. Or another way by which you can define epipole is, I can say epipole E is the image of O on the image plane pi. Okay, and the epipole E dash is the image of O dash on the image plane pi dash. Okay, so that is another way of saying it. Anyway, this epipoles E and E dash is also something that you will have to note or remember. Okay, and we will use it in the later slides as we discuss more on this particular method. Okay, now what was discussed earlier is that we saw a case where now what we saw was a case where we had assumed that we have only one particular point in the image, and we are considering only that particular point, right? Now, what we'll see is that, let's say if you have multiple points, okay, and you want to find out where exactly is the point of intersection, then what do we do about that? So if you look at this particular image, we are already familiar with what is the optical centers over here. This small p represents the image of the point capital P, which is actually the our 3D world point. Okay, and this is the image plane pi. Okay, this is the epipolar line, and this is the epipole E. Now, when we discussed earlier, we said that let's say you're considering only one particular image, or let's say you're considering different, image features or so. Now, along this line, let's say you have got different, points. That is, let's say you have P1 and P2, which are all, estimates, possible estimates, or estimates of where the 3D world point could be. That means, by calculating, we have obtained positions P2, P1, and P along this particular line. Okay, and we have to find out, which is the world point over here, right? And we saw in one of the earlier slides that here, if you are using just one single image, we know that the point would lie, the 3D point would lie along this line, but we do not know at what exact distance it is there. Okay, the distance information is not available to us, and therefore you need a second image for that, right? So let's say the second image you have is the pi dash over here. Now, for each of these 3D world point estimates that we have obtained, if we try to join that, or draw that, project that particular line, right, through O dash, what we see is, okay, I get a P1 dash, P1 dash here, P2 dash here, and small p dash here, right? So each of these are the image points corresponding to P, P1, and P2 on the image plane pi dash. Okay, and if you're considering the image plane pi, what we'll see is that the image points for the point capital P, P1, and P2 is the same. Okay, that means it would be P itself, right? So P is the image point corresponding to P2, P1, and P. But when you're using a second image and making use of the pinhole camera projection model and projecting the lines over here, what we see is that we are able to make a distinction of what is the relative distance between these points in the second image that we are considering. So in the first image, this point P has an overlap of all the points that lies along this line. Okay, but with the help of a second image, what we see is that we are able to make a clear distinction of what is the relative distance between each of the points here. Okay, so again, this is one concept that you need to remember. Okay, now let's just familiarize with cross products, right? So before going to the cross products, let's see what is a skew symmetric matrix. So let's say if A is given by A1, A2, A3, which are the elements, okay, and it's a three vector element here, or a three vector matrix here, I can create what you call as the skew symmetric matrix. So how I create the skew symmetric matrix is I denote it in this form. I write it as A with a square bracket, suffix x is equal to, and what I do is along the diagonal elements I give 0. Okay, so zeros along the diagonal elements, and for a skew symmetric, how it would be is if I give A3 here, this would be minus A3. Minus A2 becomes A2 here, and A1 becomes minus A1 here, right? So given a particular vector here, a three vector, okay, A is equal to A1, A2, A3, I can construct a skew symmetric matrix as shown over here, okay, and this is how I arrange the elements. Now this skew symmetric matrix is important because we make use of this skew symmetric matrix in order to calculate the cross product. So we know that when you're calculating the cross product, let's say you're given two vectors, which is A and B, and I'm trying to calculate A cross B. What we see is that this is how the calculation is, right? These would be the elements which are present in the final cross product, right? So this particular expression or these particular elements, it can also be found if we calculate, we can calculate that in terms of the skew symmetric matrix. Okay, and that can be done in order to reduce the computations that we are using. So that means this A cross B cross product, okay, can be written in terms of the skew symmetric matrix as shown. We can write it as the skew symmetric matrix into B, right? Or you can also alternately write it this way. Okay, let's just go with this particular notation where you say that if I take the skew symmetric matrix of this vector A and multiply that with B, I get what is the cross product of A cross B. That means I will get exactly these elements that you're seeing here. Okay, so what we'll do is when we are discussing about some methods later on, we see that whenever we are calculating the cross product, okay, in order to simplify the computation, what we do is we try to find out the corresponding skew symmetric matrix of one of the elements and just multiply that with the other element that is present. Element in the sense the other vector that is present. Okay. Now, next, so as I said earlier here, what we are assuming is that we assume that the rig is calibrated. That means we assume that the camera projection, the parameters are known, or it is already determined in when you're going about with the fusion technique, or when you're going about with the stereopsis method in general, right? So what we'll see is we'll see how we can characterize the epipolar constraint. Okay, that means the concept of epipolar geometry that we just discussed right now, we will see how we can mathematically try to represent that. Okay, so for that what we do is, again, we make the assumption that we know what are the parameters of the camera, and also we will we will just assume normalized image coordinates. That means p, when you're considering p, it's a unit coordinate that we are considering. Okay, and according to the epipolar constraint, we saw that three planes must be coplanar, right? Or that means coplanar in the sense you have three different lines, okay, which lie along the same plane. So you have OP, which represents the line joining the camera center O with the image point P. Then you have the camera center O dash joining the the line joining the optical center O dash with the image point P dash, and then you're considering another line which is the baseline. So this O dash stands for the baseline. So given these three these three lines, so now what I'm representing is, I'll just show that over here. So I have this baseline over here, and this is my OP, okay, this OP that I have, and here what I have is the O dash P dash line. So given these lines, okay, what I'm trying to say is that because these are coplanar, I can say if I take the dot product of one of these lines, okay, along with a cross product of the other two lines, I get it as 0. So this particular formula is something again which we have discussed in one of the first few classes. You can go through that once again. So what we are doing is, if you have three lines which are coplanar, I can write it as if I take cross product of two lines, okay, I get the normalized vector over here. So I get a normal or I get a line which is normal to this particular line. Therefore, if I take the dot product of these, I'll get it as 0. So I can write, okay, one line dot the cross product of other two lines would be equal to 0. Now, this same thing I can translate or I can write it or interpret it in terms of the coordinate parameters, or the coordinate the transformations that we have seen earlier. So this O is basically the origin of the camera center, right? So if I say OP, okay, I can just say it is the same as writing it with a coordinate P, okay, and I take the dot product of that. And this O dash, that is O is basically the camera center for the first camera, O dash is the camera center for the second camera, and it lies along the baseline over there, right? So it is equivalent to saying that, okay, I have taken an image, okay, at this particular point, and then that same camera system I have just translated to this particular point O dash, right? Because they lie along the same line, I can just translate that along this, and so therefore this can be interpreted as just a simple translation operation. So I can write it as T. Then cross, Here, O dash P dash is again the line joining the optical center of the second camera along with the image point in the second image plane. So if I translate this in terms of the this origin, here the origin is O dash, but if I try to interpret it in terms of the origin O, what I can say is that, okay, this is equivalent to saying that, okay, this particular point P, okay, and P dash, this P dash would be a rotated version of P. So I can just represent it by R P dash, where this R is the rotation matrix. Okay, and rotation as well as translated version, in the sense it would be a Euclidean transformation, but the transformation part has already been taken care over here when we try to incorporate that in O dash, right? So here the rotation part can be taken care of over here, and we can write it as R. Okay, so therefore this particular equation I can also reformulate that in this particular form. That is, I write it as P dot T cross R P dash is equal to 0, where T is my translation matrix and R is the rotation matrix. Now, once we have this, now this is in the form the dot product, the cross product, right? Now we saw that when we are trying to calculate the cross product over here, okay, in order to simplify the calculation, I can write it in terms of the skew symmetric matrix, right? So what I do is here I can just I can consider a matrix given as Tx bracket R. Okay, that means this point T cross this particular matrix over here. Okay, the T cross R matrix that I have over here, I can represent that by the capital E matrix, which is shown in the next slide. Okay, so instead of taking the cross product of T cross R in this case, what I'm doing is I'm just taking the skew symmetric matrix of the translation vector, okay, and then just multiplying it by R. So what I'm doing is I'm simplifying the calculations over here, and this is given by the matrix E. Okay, and this matrix E is what you call as an essential matrix, and you'll see that it's a 3 cross 3 matrix, right? And it is called as an essential matrix. So once you have this matrix here, that previous equation, you can write it in this form. That is, I can write it as P transpose E P dash is equal to 0. That is this whole formula that you have, that can be translated as shown over here. I can write it as P transpose E P dash is equal to 0, where this E is nothing but the essential matrix, which makes use of the skew symmetric matrix. Okay, now this equation that you have here is what you call as the epipolar constraint. Okay, you call it as the epipolar constraint. Okay, and this is the epipolar constraint, and what that means is, or what that says is that basically this P, okay, and P dash, they both are images of the same 3D point, capital P. Okay, and once we know what is the let's say you know what is the point P over here, okay, you can easily calculate what is the corresponding point P dash. So once you know P, and if you know what is the essential matrix, so the essential matrix would contain the camera parameters, okay, which consists of the translation and the rotation parameters. So once these two are known, you can easily calculate, or you can easily find out what is the corresponding point P dash, okay, and that is how this formula is being used, and this formula is what you call as epipolar constraint. Okay, so we can stop here. I'll just give a quick revision of what we've seen today. From today's class, we are discussing about reconstruction techniques, and we discussed that broadly there are two methods which can be used. Okay, so one is the stereopsis method, where you have two images being considered. So given two images, we try to and two images as well as the camera parameters, we can try to reconstruct the 3D scene. Okay, and the second method you have is the SFM, or the structure from motion method, where you consider consider different multiple images, and from those multiple images we try to calculate what is the 3D point or the 3D object or the 3D scene. Now, in the case of structure from motion or the SFM method, what we see is that the camera parameters need not be known, okay, and if needed, the camera parameters can also be computed, okay, from that. Now, after that, we discussed about the stereopsis method. So, in the stereopsis method, what we do is we first try to find out what are the camera parameters, and we assume that the camera parameters are known, and then we go about with the fusion technique. So basically, what the binocular fusion technique means is you are trying to identify what are the image point pairs. So basically here, using the epipolar constraint, what we do is we are trying to find out these corresponding point pairs. And once we have the corresponding point pairs, the next step would be the actual reconstruction, where reconstruction means given the corresponding point pairs, we try to find out the capital point P, okay, and that is the reconstruction method. Then we also saw some basic concepts of the epipolar geometry. So in epipolar geometry, what we consider is that given a image point P and a 3D point capital P and the optical centers over there, right? So we can say that the corresponding image point P dash in the image plane pi dash would lie along the epipolar line L dash. And we saw some terms of what do you mean by epipolar lines, epipolar plane, the epipoles, okay, what is baseline, etc. So these are some points that you need to be familiar with. And by that, we'll stop for today's class. Do you have any doubts? Any doubts so far? Okay. So what I'll do now is I'll just okay, it's 5:15 right now. The quiz would be launched at around 5:20 to 25. Okay, so I'll keep the meeting open till the quiz has been launched. Thank you. Okay, the assignment has been, I mean, the quiz has been posted. Please submit it within 5 minutes strictly. Thank you.